In this lecture, we will learn about expectation of random variable. So before going into the exact definition of the expectation random variable, let us talk about one simple example. So suppose we have a discrete random variable which takes values x1, x2, xk, and so it has basically it can take k values, and k is a known number. So, for example, you can think of a tossing of a coin, and suppose x denotes x takes value one. If a head appears, whereas x takes value zero if a tail appears. Okay. So in this case, this x random variable can take two values with positive probabilities, and in this case I can repeat this experiment again and again. So I can toss the coin again and again, and I can note down how many times head appears and how many times tails appear. So the number of times head appears is called the frequency of 1, and number of times tails appear is called the frequency of 0. Okay. So when we have a random variable x which can take x1, x2, xk values, the k values, and k is a fixed quantity, I can repeat this experiment again and again. Suppose I do the experiment n times, capital N number of times, and then I see that out of capital N number of times, fin times xi occurs. So fik is basically nothing but the frequency of xi when I repeat the experiment capital N number of times. Now, in this scenario, you know what is the meaning of the average of the value. That is nothing but the value multiplied by the frequency, and then you take the summation over all the possible values of x and divided by n. So, for example, if I try to find out what is the average of number of heads, that is nothing but number of time head occurs multiplied by 1 plus number of time tails occur multiplied by 0 divided by capital N. Okay, so this is a standard average which we knew, which we have actually learned in our school level. So now think of, if I take this n very large, what will going to happen? So if I take n is very large, that means n goes to infinity. Clearly, this is nothing but the limit of this quantity, then this n put inside. So I can write it is the frequency divided by n. So this quantity frequency divided by capital N. This quantity is basically nothing but the proportion of times I observe xi out of n trials. Okay. So now, because this is a finite sum, I can take the limit inside. Xi does not depend on capital N term outside. So I have this quantity, and if you see this limit is nothing but the long run proportion of xi, which is intuitively nothing but probability of xi. So that's why I write it, the limit equals to pi, which is nothing but probability of xi. So what I get if I take n tends to infinity, if I do a very large number, I repeat my experiment very large number of times, and then if I see what is the average of all possible values that I have observed, that is nothing but can be represented as summation xi I equals to 1 summation xi into pi. Okay, that can be represented as summation xi into pi, which is basically nothing but summation x value multiplied by the probability that x taking that particular value. And this quantity in general is called the expectation of x. So expectation of x is nothing but long run average of the value that are assumed by a random variable. So the definition of the expectation is given by this, that let x be a discrete random variable with probability mass function fx and support sx. The expectation or the mean of x is defined by expectation of x equals to summation x belongs to x support of x fx, provided this summation is finite. I'm coming why I need this condition, I am coming to this. But before that, note that this expectation is basically nothing but the value taken by the random variable, discrete random variable x with positive probability multiplied by the corresponding probability. The PMF is nothing but the corresponding probability. So this quantity is exactly of the form xi pi. So this expectation, which is also called mean, is nothing but the long run arithmetic average of the values that are taken by the random variable x with positive probability. Okay. Now, why I need this condition? This condition I need because you know that if I talk about a series of the form xn n equals to 1 to infinity, this series converges if, or I write um, if summation mod of xn converges. Okay, that is basically this series converges. This series converges basically mean that the partial sum, which is basically summation xi I equals to 1 to n, this partial sum converges. This partial sum converges, the partial sum of this series converges, then if and only if this quantity is finite, which again basically means that you take all the sequence of partial sums of this particular series, and that will have a finite limit. Okay, clear? So that basically that the same thing actually we are using here. Note that here also this sum could, because when Sx is finite, we do not have any problem. This always converges. But when Sx is a countable set, a countable infinite set, then we can have a problem. This sum can convert, may convert, may not convert, and in that particular case, we need to check that whether this sum converges or not. If this sum converges, which basically means that this sum converges absolutely, and when this sum converges absolutely, this sum itself converges, so this condition is kept there. So this condition is kept there solely because of to check to confirm that this sum converges. Okay, and obviously, as I already pointed out, when support is finite, we do not need to check that whether this is finite or not, because this has to finite. But when support is infinite, we need to check, obviously infinite means countably infinite, then we need to check that if this condition is true or not. And when this condition is not true, that means this summation is equals to infinity, then we say that the expectation does not exist, or sometimes we say that the expectation is infinite. Okay, so the expectation for a discrete random variable x is defined by summation value into the probability mass function at that value, and we need to check whether it is absolute convergence is there, or whether the absolutely convergence is there or not. If it is absolute convergence, we are fine. If not, then we say that the expectation does not exist, or sometimes we say that expectation is infinity. Okay, fine. I hope this intuitive meaning, the physical meaning of the expectation and the definition is okay with everyone. So let us see some of the examples now. So first start with one of the simplest examples where we roll a die, and if we roll a die, x denotes the outcome. Outcome means the number of dot on the upper face, and then the probability mass function of x is nothing but it takes one value 1 by 6 for all values of 1, 2 up to 6, and it takes value 0 for all other values of x. And in this case, obviously, it is this is a discrete random variable. That's why we are talking about the PMF. And in this case, if I try to find out the expectation of x, I basically need to check that what is the sum. I basically need to check that. So example 2.21. Example 2.21, we roll a die, and we need to see that what is the expectation. So in this case, by definition, expectation is equals to summation x belongs to Sx, x f of x. And in this case, as we have already seen, that support is nothing but the set 1, 2 up to 6. It is a finite set, and we have seen that f of x is equals to 1 by 6 if x belongs to Sx and it is 0 otherwise. So that basically means that this sum is over a finite range. So obviously the absolute convergence will be there. We do not need to check even the absolute convergence in this case. And we can write this quantity is equals to x equals to 1 to 6. The value x multiplied by PDF, which is constant 1 by 6, so multiplied by 1 by 6. And if you do the summation, it turns out to be 3.5. Okay, so in this way we will be able to find out what is the expectation, and that is exactly given here. Well, I have shown that in this case that basically if you see the absolute sum, which is basically again a finite sum, so it has to be finite, no other option. So in this case, expectation exists and expectation is 3.5. And one thing you should note that the random variable x do not take the value 3.5. So the probability that x equals to expectation of x in this particular example is exactly equals to 0. That's always not true, but why I put this one, I want to just stress this one. Expectation is not a value which is assumed by the random variable. Okay, so that particular value may be assumed by a random variable, may not assumed by a random variable. So I hope that this example is simple and understandable. Now let us see next example, which is binomial one, which is again in this case my support is finite. So I do not need to check the existence condition. The expectation exists always, and when expectation exists, I can calculate the expectation as summation x, and this part is basically this ncx p to the power x 1 minus p to the power n minus s. This part is basically probability mass function. So it is the product of x into probability mass function, and take the sum over the support, which is 0 to n, which is 0 to n. So once I have this one, I can do the sum easily. It's not a very difficult one. And finally, we got that the average, the expectation is NP. And note that this expectation is very, very meaningful in the sense that, see, in case of the Bernoulli trials, the background of the binomial experiment, which is Bernoulli trial, I am repeating the Bernoulli trials for n number of times. And what is P? P is the probability of success. So when I repeat the same trial for n times, it is expected that there will be NP successes. Okay, out of small n number of trials, there will be NP successes, n multiplied by p times successes. So that is basically my average. And so this average is very, very intuitive value, and we can easily intuitively say that, well, expectation is a meaningful value in this case, meaningful average in this case. Let us talk about now another example, which is geometric one, and in case of the geometric, the support is not finite. So clearly, when support is not finite, I first need to check whether this quantity is finite or not. And in this case, this checking is very, very simple. The reason is nothing but the support, all the elements of the support are positive. So keeping this mod and removing this mod is basically same for this particular example, because we are taking the summation from 0 to infinity. Okay, and so I first remove the mod, then that 0 do not contribute anything in the sum. So the sum become x equals to 1 to infinity xp 1 minus p whole to the power x, which you can simplify into this form by writing 1 minus p equals to q. Now it is very easy to check this sum converges, because the partial sums of this series is basically nothing but this, which converges to p by q by p square. So this sum converges, and fortunately in this case the expectation also nothing but this summation, and you can see this summation is nothing but p times q by p, which is q by p square. Okay, so in this case the expectation is 1 minus p by p. So number of failure before the first success, average value of the number of failure before the first success is nothing but Q, which is 1 minus P by P. Okay. Similarly, you will able to do the Poisson case. I left it as an exercise, but keep in mind that for Poisson case, the support is countable infinite. So you first need to check whether it is absolutely convergent or not. Absolute summation mod x fx is finite or not. That you need to check first. And once you can show this is finite, you will be able to find out what is expectation of x and check that whether you are getting expectation of x equals to lambda or not. Now let us consider one case, at least one example where expectation do not exist. Okay, so to do this one, consider this function. What is this function? This function is nothing but for each x belongs to the set of natural numbers, if the value of the function is c by n square, c is a constant which is given by this, and it is 0 otherwise. So what does this mean? This basically means that, example 25, 2.25. So we know that summation 1 by n square converges. Right? We know that summation 1 by n square converges, and suppose take as this thing converges, so this one I can take that I equals to n equals to 1 to infinity 1 by n square equals to c, and this assignment, this c is a finite quantity. Okay. Now if I define a function by taking this, okay, it is basically not c, I take this the inverse of this quantity. Okay, inverse of this quantity c, and now if I take a function fx which takes value c by n, if n equals to 1, 2 and so on and so forth, c by n square and 0 otherwise. So naturally now if I take the sum of the function over x equals to 1 to infinity, which is basically summation, well, this will be x, well, this will be x, and this will be x. So it is x square, here also x. So this quantity is nothing but c by x square, x equals to 1 to infinity, and which is basically c summation 1 by x square, x equals to 1 to infinity. Now what is c? C is nothing but exactly reciprocal of this summation. So that means this quantity is 1. Moreover, the function f is strictly greater than equals to 1, x is strictly greater than equals to 1 for all x belongs to, strictly greater than equals to 0 for all x belongs to R, and we have a countable set on which the function is strictly greater than 0 and the function is strictly greater than 0 on x belongs to the natural set of natural numbers, and when we take the sum of the set of the natural numbers, it turns out to be 1. So clearly this function is a probability mass function. So now let us consider x is a random variable which having this probability mass function. So if I take this one, you can see that this is a probability mass function, and suppose we are trying to find out what is the expectation of that particular random variable which has this probability mass function. So as the support is countably infinite, first I need to check whether this quantity is finite or not. And when we try to check this quantity is finite or not, that basically means that again the support is the sum is over x equals to 0 to infinity. So I can remove the modulus from here, and if I remove the modulus, 1x will cancel out 1x from here, and I have this summation is nothing but c summation n equals to 1 to infinity 1 by n, and we know that this quantity does not converge. Summation 1 by n does not converge, and that's why the expectation in this case does not exist, or as I said, sometimes we say that the expectation is infinity. Okay, the expectation of infinity we do not say always, but more general terminology is that expectation do not exist. Okay, so in this particular example, when a random variable x has this probability mass function, the expectation do not exist, and I hope that you have understood that why expectation do not exist. Okay, I stop here in this lecture. In the next lecture, we are going to talk about expectation of continuous random variable. So we have already talked about expectation of the discrete random variable. Now we have to talk about expectation of the continuous random variable.